Hello friends, in this video we are going to discuss about the effect of light on N-type semiconductor. So let us consider a N-type semiconductor bar. So this is an N-type semiconductor bar. In this case, this N-type semiconductor bar is it at equilibrium condition. That means no light or no external energy is falling on the N-type semiconductor. Now, at this equilibrium condition, we can say that there will be some thermally generated electrons and there will be some thermally generated holes inside the N-type semiconductor, because we have considered that the temperature of this N-type semiconductor is at room temperature, that is 300 Kelvin. Let us assume that the total electron concentration inside this N-type semiconductor is N suffix N, and the total hole concentration at the equilibrium condition is P N. Since it is an N-type semiconductor, so we can say that the electron concentration should be very much greater than the En, that is, the electron concentration Nn should be very much greater than the hole concentration Pn. That's why it is a N-type semiconductor. Now, let us consider that we have incident a light on the semiconductor, and this semiconductor is a N-type semiconductor. So we can say light is being incident on this N-type semiconductor. Now, as we know, this light is nothing but the photon particle stream, photon particle stream, and each of the photon will have energy E equals to h nu. So we can think that photon particles are streaming and incidenting on this semiconductor. Now, due to these photon particles, some covalent bonds will be broken at this part of the semiconductor. So there will be some excess electrons and holes will be generated. So let us assume that del n is the excess amount of electron that will be generated inside this N-type, and del p will be the excess amount of holes that will be generated in the N-type. Now these electron and holes are generated in pairs, so we can write that del n, that is the excess electron concentration, should be equals to the excess hole concentration, because electron and holes are produced in pairs. So the excess electron concentration should be equals to excess hole concentration. Now, due to this incident photon, some covalent bonds has been broken. So equal number of electrons and equal number of holes are being produced, and these equal number of holes and electrons are called excess carriers. Excess carriers. That is this is excess electrons, excess electron concentration, and this one del P is the excess hole concentration. And in common phrase, we say that it is a excess carrier concentration. Now, If we see the total concentration of electron right now, that is Nt, is the total concentration of electrons after light incident is equals to, previously there was Nn number of electrons before the incident of light, and after the incident of light some excess electrons has been generated, that is the del n. Similarly, if we find the total hole concentration, that is the total concentration of holes after light incident, is equals to, previously before the light incident it was Pn, and after light incidence an excess hole concentration del P has been produced, so Pn plus del P. According to low level injection, low level injection. So what is low level injection? Low level injections means if the excess carrier concentration, that is del N and del P, these are the excess carrier concentration, should be very much less than the majority carrier concentration Nn before the light incident. If it happens, then it is called the low level injection. So let us assume that low level injection has been taken place. So for that case, we can say that the total concentration of the electron after light incident will be nearly equals to Nn, because this del n is very much less than Nn, so we can neglect the del n term. But the total concentration of the hole after light incident will be Pn plus del P, because Pn and del P are comparable to each other. So we can say right now that under low level injection, the total electron concentration Nt will be equals to Nn, nearly equals to, and the total electron concentration was Nt, nearly equals to Nn, and the total hole concentration is will be equals to Pn plus del P. So in this way we can see that the majority carrier concentration, that is the electron concentration, because we have considered the N-type semiconductor, and in the N-type semiconductor the majority carrier concentration is the electron concentration, and this is the minority carrier concentration. So we can say that due to the incident of the light, the majority carrier concentration do not change by a significant amount, but the minority carrier changes by a significant amount. So we can say that the percentage change in majority carrier, that is electron concentration, will be negligible, but the percentage change in minority carrier, that is the whole concentration, will be large. So we can say that when light incident on a N-type semiconductor, the whole concentration will change by a significant amount, but the electron concentration will be same, because the percentage change in the majority carrier will be negligible. Now let us assume that this Gn is the generation rate of excess electron inside the N-type semiconductor after light incident. Similarly, Gp is the generation of excess hole inside the N-type semiconductor after light incident. Since the electron and holes that has been generated, that is the excess electron and holes are generated in pairs, so we have seen that del n, that is the excess electron concentration, is equals to the excess hole concentration. So we can say that Gn, that is the generation rate of the excess electron, should be equals to the generation rate of the excess hole, and the unit of this generation rate, that is the Gn unit, will be electron hole pair, that is the EHP per centimeter cube, that is per unit volume per unit second. Similarly, Gp will also have unit electron hole pair per unit centimeter cube per unit second. In this way, we can say that the generation rate of the excess electron is equals to the generation rate of the excess hole. Sometimes this is also called optical generation, the optical. Sometimes it is also called optical generation. So we can say that Gn is equals to Gp and it will be equals to G optical. So this is how the N-type semiconductor behaves after the incident of light due to non-equilibrium process. Thank you.